Right, so now we solve an initial value problem, which is the differential equation plus the initial condition. So basically you are saying I want my solution y to pass through the point 1 minus 1 minus 1. That's also it's a specific solution. Remember, when we solve the differential equation plus the initial conditions, we get the general solution, which is a family of solutions. So when we now specify the point where the graph, the solution should go through, then we have only one solution, and that solution is very specific in terms of where it passes through. It passes through a specified point. All right, so how do we solve this? So for now, you ignore the initial conditions and solve it as if you don't have initial conditions. So you need to get the general solution first. So again, with this one, I see that I have an opportunity of factorizing y there. And with this form, then the next step is to separate the variables, divide by y, divide by x squared, multiply by dx, and then do your algebra, and then you get to this point. And then at this point, I now have this solution here, but I want to make y sub the formula. So basically, I need to apply the exponent both sides. So I have e to the power ln of y is equal to e to the power minus 1 over x minus ln the modulus of x plus c. All right, then on the left hand side I have y. On the right hand side I have e to the power minus 1 over x times e to the power minus ln the modulus of x times e to the power c. So this is a constant, I can call it a. But here I can then see that e to the power minus ln of x is equals to e to the power ln of 1 over x, which is just 1 over x. So then I now have this is equals to e to the power minus x, minus 1 over x, sorry. E to the power minus 1 over x times a over x. So I have that solution. Now, what I did here, I just tried to play around with laws of logarithms to get to this point here. So I took ln the modulus of y plus ln the modulus of x is equals to minus 1 over x plus c. Then on the left hand side now I have using laws of logarithms, ln of y times x. That's what I got there. And the right hand side remains the same. And whether I use what I used there or I use this, I just get to the same solution. It's the general solution because I have the constant of integration here. All right. So now after the general solution, then that's when we apply the initial conditions. So let's have y of minus 1. So basically here I have y of x. So all I do is to say y of minus 1, but what is it equal to? It's already equal to minus 1. So the left hand side is equal to minus 1. Then on the right hand side I have a, then e to the power minus 1 over minus 1 over minus 1. So then it becomes e to the power 1 over minus 1. If I multiply by minus 1, then it gives me 1 is equals to ae. So then I make a sub of the formula. Remember, when I apply initial conditions, I'm trying to find the constant of integration. So the initial conditions are used to what? To get to obtain the constant of integration. Okay, so that's what you need to know. So I have my a, I come now back to that general solution and replace a with e to the power minus 1. And of course here now I'm just playing with laws of exponents. And whatever I get, this is just a specific solution that is going through the point -1, -1, and we call it a particular solution. And the question is, can you find the interval of definition here? So I will then basically say, look at this solution function here. It's not differentiable at x is equal to 0. It's not defined also at that point. So we then have to say this is the interval from -infinity to 0, open interval union 0 to infinity. So that's the solution, the interval definition of the solution. And there we are, we're done. So all the other questions that you get under this specific method, they will all be going through. It's either you just need to do something to get to see that it's separable. And then once you see that it's separable, then you separate the variables. And once you separate the variables, you then now integrate to get the solution. So different forms of differential equations will be given to you. Some will be having trigonometric functions, some exponential function, the mixture of those, and the technique actually lies in identifying that it's a separable equation. That's number one. Number two, separating the variables. And then number three, applying integration. And then number four, wherever possible, you now have application of initial conditions. But you can see we can also link this to continuity. So we will then say, make sure that the solution is continuous in a specific interval. So then you then look at that function that is the solution. You then test your continuity, the continuity of the function at certain points that are defined, that are specified for you. So it's just one method to one thing to just solve the separation of variable, but the method can be linked to several different concepts that we have done so far. And of course, we might ask you to draw the solution curves before you solve it. We just say draw the direction field. So the direction field can be drawn for any differential equation, whether you can find the solution or you cannot find the solution, the exact solution. But yeah, it's usually most useful when there is no exact solution to the differential equation. But you can mix all of those different concepts. So this is now where we will then test for deep learning. So we see how you can connect these concepts and link them together and execute. So that's what I just wanted to emphasize in this case. Okay, see you.